All right, this video we're talking about magnetic flux, only this one section. We have to talk about this before Lenz's law and Faraday's law, because both of those two topics involve magnetic flux. So we did something very similar back when we talked about Gauss's law. Right before Gauss's law, we talked about electric flux. And the definition here is going to be very, very similar. So we want a definition that keeps track of like how much. So notice, by the way, this is a loop, but we're just looking at it from the side, right? So yeah, this is either like a rectangle or a circle or something that we're just looking at from the edge. So here, the magnetic field is totally going through that loop, right? We want some non-zero value of flux for this, but for this we want zero. There's zero flux. There's no magnetic field that's piercing through that loop. So in terms of the normal vector, so notice how this is the normal vector to all of these. It's when the magnetic field is parallel to the normal vector that we want the full amount of the flux. And when the two are perpendicular, there's zero flux. So in this case, the magnetic field is parallel to the plane of the loop. And another way of saying that is that the magnetic field is perpendicular to the normal vector of the loop. So this is sort of an intermediate case in the middle right here, right? So there's some magnetic field passing through the area, but not as much as this one. So it turns out what's relevant here is we want like the dot product between the normal vector and the magnetic field. So yeah, the book spends forever motivating this, but we already did this with Gauss's law. So maybe it's in case you weren't comfortable with it back then. The point is here, though, that this is going to be the definition we have. So if B is constant over the whole loop, if B is constant, we can write down this formula. More generally, if B is not constant, yeah, your book does it later. So if B is not constant, normally you would have to split it up into a bunch of little pieces, dA, do B.dA for that piece, and then sum up all the contributions. So this is if B is not constant. B not constant. Okay, so this dot product is just the magnitude of the area of the loop times the magnitude of the magnetic field times the cosine of the angle between the normal vector of the loop and the magnetic field direction. So this takes into account all of so these properties that we wanted right here. So for this would be cosine of 0 degrees. This would be cosine of 90 degrees and cosine of some angle in between. So this quantifies exactly how much magnetic field is passing through our surface. And it's just the dot product between those two, between the area vector and the magnetic field vector. All right. There's something that's a little different from the electric field, and that is the units here. So we already have units for magnetic field, Tesla. SI units for magnetic field, and the SI units for area is meter squared. And actually, if you just have this special combination of units, Tesla times meter squared, we have a new unit for that, and that's called a Weber. Watts is already used for capital W. So for Weber, we don't use W, we use WB. So the SI units for magnetic flux are Webers. Just a random fact that you should probably be familiar with. And I think that's it. So, this example is actually requires an integration, as you might notice from the solution here. The reason for that is that the magnetic field next to an infinitely long wire, so here we have current that's going down. The magnetic field is stronger next to the wire versus farther away from the wire. And you'll see this, the dots are closer together, closer to the wire than away. So here you can't just take magnetic field times area, because which magnetic field would you take? The one over here, closer to the wire, or the one over here, farther away? So here you actually have to split up your rectangle into a bunch of strips, where each strip has the same amount of the magnetic field. So you might write your so the flux here would be an integral of B.dA. And the magnetic field is it's constant along each one of these strips. So we probably would just want to parameterize this in terms of x. So this is what they did here. So, so our dA, so first of all, we can get rid of, here the magnetic field is passing totally through the loop. Like if we have b times a times cosine of the angle between it, it's 0 degrees. Cosine of 0 degrees is 1. So we can just do b times dA. So we don't have to worry about that. And then for this dA, we're going to split this up into a bunch of rectangles. It looks like each rectangle has, well, this b is going to be the same for every little rectangle. And then it's going to be dx, and we're going to integrate as x goes from some value to some value plus the width of the loop, x naught to x naught plus a. So this part's the dA, and then we still need the magnetic field as a function of x. So you probably want to do x equals 0 at the location of the wire, and this would be mu naught I over 2 pi x. And it depends, so this would be x naught, and then x naught plus a. So it depends on where that loop is. You know, the closer to the wire it is, the more flux that you're going to have versus farther away. But this is how you would go about setting up an integral for that. Okay, so take a look at that example. Make sure you understand how to do that. So maybe you could try, based on what I said, you could try to finish it up. Or if it still doesn't make sense, you know, go in detail through that example. Here, this is an easier one because we have a constant b. So if we actually calculate the flux for this one, we would recognize that we have a constant b and just immediately go to this formula. So because b is constant, so maybe you could always do this. This formula is always true. And then if b is constant, you can take it out of the integral. So this is because b is constant. And then b dot integral dA is just a. This is b times a times cosine of the angle between these two vectors. So here it looks like we have a 1 Tesla field. We have a 1 meter square area. And then we want the angle between the normal vector and the magnetic field direction. So this angle is actually 60 degrees, right? The labeled angle here is 30 degrees. That's the angle of the magnetic field with the plane of the loop. But that's not what we want. We want the angle with respect to the normal vector. This is cosine of 60 degrees. So it's 1/2. It looks like we get 0.50. I could write Tesla meter squared, but we learned our new unit is Webers. So half a Weber is the magnetic flux of this thing. So our next few videos are going to be talking about magnetic flux. So we have to know what we mean by this. So magnetic flux in Webers is exactly this quantity. How much magnetic field is passing through some surface.